Okay, so a lot of times they want us to be able to graph a piecewise function. So in this case, in this example we have 3 pieces, okay, because there's 3 lines there, right? All right, and I'm going to color coordinate it so you can hopefully match it up a little bit. The first piece says, okay, if x is less than or equal to 1, we're going to use x squared. Okay, so let me scroll up a little bit. So what I'm going to do is I'm going to think about f of x equaling x squared. And I'm going to make a little table of values. It's not going to be very big because my graph paper is not very big. Okay, so I want numbers that are less than or equal to 1. So I could have like -2, -1, 0, 1, right? Okay. Now those are all less than or equal to 1. So if I put in -2 and I square it, I get 4. If I put in -1 and square it, I get 1. If I put in 0 and square it, I get 0. And if I put 1 in and I square it, I get 1. Now we should know that this looks like a parabola because it's one of our basic functions, right? Okay, but let me graph those points. -2, 4, -1, 1, 0, 0, and 1, 1. Now I want to talk a little bit about that last point, 1, 1. This is going to be closed dot. And the reason it's closed, I'm going to erase my part of my little orange line there, is because of that equal to part, okay? It's less than or equal to 1. So actually at 1, we're going to be using x squared. So this part of the function looks like that. Now, why do I have an arrow here? Well, because any number less than or equal to 1, like I could go to -100 or whatever, so that keeps going on. Why don't I have an arrow there? Because I'm stopping at 1. It says less than or equal to 1. Okay, so let me get those out of my way. All right, now the next part, I'm going to do in green. So 3 if x is between 1, greater than 1, but less than or equal to 2. Okay, so we're going to say f of x is equal to 3. That's a constant function. And I'm going to start at 1. And you might be saying, wait a minute, you can't start at 1. I'll tell you why I have to in a minute. I guess I'm going to stop at 2. Okay, so at 1, I'll get out a 3, right? And at 2, I get out a 3 because it's the constant function. I'm just going to get 3 out. Okay, but my thing is at 1, it's open. It's going to be an open dot. Because I can't have it actually equal 1. And I have to think about the number like 1.009. Okay, so I have to use the 1 because I can't list all the numbers between 1 and the next number, right? I can always find one in between. So I have to use the 1, but it won't be a solid dot. It'll be open. And I'll tell you why it has to be that way in a minute. But I'm not including the value 1. And then I can have numbers like 1.009, 1.5, 1.7, 1.8, 1.99999. And I can have 2. It can equal 2. So this is going to be closed. Now, I usually like to write open and closed on my table of values so I'll remember how to graph it. Okay, so I'm going to go to 1, 3, and I'm going to make an open dot. And then I'm going to go to 2, 3, and I'm going to make a closed dot. And then all those in between. So it's just a little piece of the graph. Just want to make sure I see that it's an open dot at 1 and a closed dot at 2. Now, it has to be an open dot at 1 because if it didn't, it wouldn't pass the vertical line test and it wouldn't be a function. Okay, so just so you know, it has to go along with that. Okay, now let's look at the last piece. And it says if x is greater than 2, it's just going to be the identity function, right? All of these are examples of our toolkit functions. So I just want to think of some numbers that are bigger than 2. But I'm also going to include 2. If I put in 2, I get out 2. That's going to be open, though. It's going to be an open dot because it's got to be greater than 2, like 2.001 or something like that. Okay? And then I could have 3 and 4, and I could think of more numbers if I wanted to. But so you put in 2, you get out 2. You put in 3, you get out 3. You put in 4, you get out 4. That's how the identity function works. Okay, those keep going. All right. So 2, 2 is going to be an open dot, and then 3, 3, and 4, 4, and I can keep going. It's going to look like that. Is that a crazy graph or what? But I think these are so much fun. You just have to take them one piece at a time, okay? And then remember, if it's equal to, you're going to have a closed dot, but if it's just less than or greater than, it's going to be an open dot. Okay, now, if you think you've got this, go ahead and try it. Stop the video and try the next example. I'm going to do the next video, though. Come back after you try it, and then we'll see how you did. Okay? All right. So here's the next one, because I thought maybe you could use another example of this. And I'm going to do it similar to what I just did on the last one. So I'll start with orange. So x cubed if x is less than -1. So I'm going to say f of x is x cubed. And the points that I get to put in, I got to think of things less than -1, and I'm cubing it. So I'll just say -2 and -1. And even then, I'm going to probably run, oops, I'm going to run out of room a little bit here. If I put in -2 and I cube it, I get out -8. If I put in -1 and cube it, I get out -1. That's going to be an open dot, though, at -1 because it's less than or equal to -1. So I get a point here, -1, -1, but it's open. And then -2, 8, I don't know, it's like down there somewhere. So it's coming up like that, kind of. All right, let's do the green part. So f of x is equal to -2 if x is between -1 and 4, but not including. I mean, they're both going to be open, right? So I would use -1. This is a constant function, so you don't really have to do a bunch, but you can. 0, 4. You could use 1, 2, and 3 if you want to, but I'm not going to do that many. The output's always -2 because this part's a constant function. But this is going to be open, and this is going to be open as well. Okay, so -1, -2, so it's going to be open there. Then we have 0, -2, oops, and 4, -2 like that. Now, you know, both of these examples had a constant function in the middle. It doesn't have to be that way. It's just what they gave us. But, so it looks like that. And you might think it's kind of weird, maybe, that there's an open dot at -1 on both pieces. That is a little weird. It means this function is not defined at -1. Okay, that's all it means. Okay, and the last piece, square root of x. So f of x is equal to the square root of x if x is greater than 4. So we're going to use 4, but that's going to be open. Square root of 4 is 2. And then, boy, our next one would be like 9, which would be way off there. I could put in 5. Let me see what the square root of 5 is. I think it's like 2 point something. I'm getting my calculator. Square root of 5. Oh. Square root of 5. 2.2. And what's the square root of 6? Square root of 6. 2.4. Okay, well, I just have to approximate them. I mean, the next whole integer would be square root of 9, but anyway. All right, I was hoping to get a little differentiation. So 4, 2, and I said that was open. Oh, I only go to 5, so it's going to be like 2.2 or something like that. So it's going to be going off that way. Okay, and again, this function's not defined at 4, but which is okay, but just so that you know. Now, that's what it would look like. I don't know if you got that, but it was different. If they asked you what the domain was, just pretend, the domain would have to be from -infinity to -1, union -1 to 4, union 4 to infinity, because it's not defined at -1 and 4. I just am throwing that in though, just as bonus information. I won't even talk about the range. That would be even more different. Okay, so we'll stop that.